Fluids behave quite differently at the microscale, and this enables us to do experiments that we would not otherwise be able to do. In a laboratory at the moment, we have 3 focus areas of research, which all have a common requirement for producing spherical capsules. The first is in nuclear fusion energy production, where we need small capsules for putting the nuclear fuel in. The second is where we're making protocells or artificial cells for studying membrane protein interactions. And the third is where we're studying the encapsulation of the stem cells to go in the spinal cord to repair your damaged spinal cord if you've been in a car crash. A microfluidic system can be compared to, say, a large-scale plumbing system, say in this building, but reduced in size onto a chip. Very small tubes delivering fluids to different types of sensors and other actuators in the system.
So we can design small circuits to move around small volumes of fluid, generally using techniques borrowed from the microelectronics industry. Recently we started using 3D printing to make these microfluidic devices, and that has many benefits because it enables us to make microfluidic devices very rapidly, so we can iterate and make new designs and improve upon those designs very rapidly. It also enables us to make things cheaply, and because these printers are cheap and affordable, it's a technology that we can share with our collaborators and bring microfluidic technology to other people and other researchers who wouldn't otherwise be using it.
Traditional microfluidic techniques require very expensive equipment and also a great deal of knowledge of how to use that equipment, and so that puts a lot of people off. Whereas 3D printing, you just need to be able to design something on a computer, which is fairly simple to learn, and then press a button and walk away, and then you come back and your device is ready to use. It's also quite beneficial in that you can incorporate it with other more traditional techniques quite easily. You can plumb it into using existing fittings that are readily available. We began with a very simple microfluidic building blocks, just tubings and junctions and things, and then from there we expanded that to a wider range of different types of microfluidics. And we used those different designed systems to make a modular system that's based on Lego that anyone can print out and click them together and make their own microfluidic systems. Previous researchers have discounted this type of printing because they found that it leaked or they couldn't see through it. But by refining the print characteristics, I found that if you avoided under extrusion, you could make the devices both transparent and watertight. To avoid under extrusion, you have to print quite thin layers and you have to print quite slowly. So talking 50 micron layers and at speeds of 13 millimeters a minute or less. The same techniques that make them watertight also beneficially make them transparent, because the gaps in between devices are what cause you to lose transparency.
So we're pleased with what we've been able to achieve with 3D printing for microfluidics so far, but what we're really looking forward to is as the diversity of materials with which you can print expands and the resolution of the printers improves, being able to make not just fluidic circuits, but integrate optical and electronic components also. This will enable us to print multifunctional devices from multiple materials in one single device. So we're working with researchers from a range of fields around the world, and 3D printing really allows us to be able to send a design to another laboratory. So we're working with people in Italy, for example, and we're able to send them designs that they can print out in their labs and conduct experiments and report back those results the very same day. It really makes the process much simpler, and so that everyone can really access the benefits of microfluidics.
Well, the beautiful thing about 3D printing is that potentially everybody can have them. Any other walk of life, say a hospital, biological laboratory, anywhere really, everybody can use them. It democratizes the technology of making things.